this morning as an expert in counter chemical and biological weapons defense. Take it away, Ben.
All right, so I'm going to, first of all, is my audio coming through okay? Can everybody hear me okay?
Yep.
Great, okay. I'm gonna go ahead and share my screen. Bear with me 1 second. Let's see. Can everyone see that now? I'm gonna go ahead and go full screen. How's that look?
Looks perfect.
Great, okay. So thanks, Amna. So again, my name's Ben Ervin. I'm a group leader or assistant group leader, I should say, at MIT Lincoln Laboratory in the Counter Weapons of Mass Destruction Systems group. So Amna and I worked together on creating systems that defend us against chemical and biological attacks, as well as working to try and secure the nation and make the nation resilient against pathogens that could cause pandemics like we're in right now. And so today's talk, I'm going to go through some of the just sort of introduction to disease propagation. When I say propagation, I mean spreading of disease. Okay, propagation is just sort of movement. And so I'm going to talk about generally some of the characteristics that go along with infectious disease. And then we're going to get into some of the modeling. I know you guys are doing serious gaming and maybe related to zombies. And so I'm going to set the foundation for modeling that is associated, that can be transferred over to modeling zombies and how they attack and propagate and disperse more zombies throughout society in some sort of apocalyptic situation. So to start off with, I kind of wanted to give you the bottom line up front. We call these bluff sides. The idea here is infectious disease, things like COVID-19, things like AIDS that move through society. They're highly complex, and it's a highly variable process. So when somebody says, "Oh, if you do this, you might get sick," it always depends on several different factors. So you have to look at the pathogen type that we're discussing. You have to look at the environment that you're in, the individuals involved. Somebody that's older and immunocompromised is going to be different than somebody that's in the military and at the peak performance, physiological performance of their career. And then we have to look at social measures. So right now, as you're all aware, we're all at distance right now as a social measure. We wear masks in stores. Hopefully you're wearing masks in stores. We're distancing ourselves up to a certain amount. Those are all things that we're trying to do to reduce the amount of spread of the infectious disease. Some critical questions that we're going to cover today and lead into the modeling effort is the amount of dose that it takes to become sick. So if you are around somebody that's coughing directly into your face, you're going to get a larger dose of whatever they're infected with than if you're just peripherally 20 feet away and there's a small particle that maybe moves across with the air system. Infectivity is a big issue. So when are you infectious to others after you yourself have become infected? As many of you are aware, COVID-19 has a long delay between when you're infected and when you actually show signs and symptoms. In some cases, you might not ever show signs and symptoms, but you might be infectious to other people. And so that infectivity is very critical. Spread of this, so is it person to person or is it sexually transmitted, for instance? Are you infected via fluids? Do mosquitoes move it? Those are all critical questions for infectious disease propagation. Incubation, how long do you have it before you know that you're infected? And then the mortality rate, everyone's obviously interested in. If you have something like Ebola, it's sort of a dice roll as to whether you're going to live from that, depending on where you're at in the world, as opposed to COVID-19, which is below 10% in most cases, depending on your health. To that point, there are a range of infectious disease models that you could use for your game in order to model these types of things. You could use something that's a very highly accurate computational model that is very intensive, but it answers a very specific question. So for instance, if you're a bank teller, is the setup that they have for you going to reduce your risk of becoming infected if somebody walks in that's infected? As opposed to compartmental models, which is what we're going to look at today and what you will probably use for your zombie game, which answers kind of broader questions and shows the peak of infectivity over time. All right, so I wanted to talk just briefly about disease and pathogens generally. So a disease, the general definition of it is just a disorder or of a function in a human, animal, or plant that results in some sort of a physical injury. So that's very broad. And the most common diseases for humans are heart disease, cancer, Alzheimer's, that sort of thing. We're not talking about that today. And that's not what we're talking about with the zombie apocalypse either, really. We're talking about a microorganism or pathogen-based infectious disease that can be transferred from person to person. And really break this down into about 5 microorganisms that people generally discuss. Viruses, which is what SARS-CoV-2 is, and HIV. You have bacteria, which is, we'll be using Bacillus anthracis, which causes anthrax as our example today. And then those will focus mainly on virus and bacteria, but the other ones are funguses, which mushrooms are the most widely known, but there are many more that are much smaller than that. Protozoa, and then things like worms, so tapeworms are things that can get into through drinking water and such in other countries. We don't have as much of an issue here in the United States, but certainly something that causes disease internationally. And so we'll talk a little bit about viruses and bacteria in more detail in the next slide. So viruses, essentially, there's debate over whether they're actually living or not, but for all intents and purposes, we'll say they're not living. They basically exist to just replicate themselves. So they get into a living cell, and they trick that living cell into making more of the virus. And so what I've done here, can everyone see my cursor? Can you see this? Okay, so you basically start off with a living cell, and the virus attaches itself to it. So think of this as SARS-CoV-2. It attaches to your cell, and then it penetrates into the cell membrane, and it injects its RNA into it. And then it tricks the cell into making more of that RNA, and then it creates more of the coronavirus, and then it starts releasing it. And there's a picture here. This is an actual picture of a living cell on a plate with coronavirus essentially being replicated and spit out of that living cell. And so that's what's going on with COVID-19. It keeps creating more and more of itself inside, and then you shed those particles and you infect other people. The size here is very small, 10 to 500 nanometers for most viruses. SARS-CoV-2 is around 100 to 200 nanometers. And it moves through generally saliva, mucus, blood, that sort of thing. When you cough out or sneeze or even breathe, all those things have infectious viral particles in it if you're infected. And then on the bacteria side, we're talking about something that's about 10 times or more in size from the viruses. And it uses something called binary fission to replicate itself. So instead of getting into a living cell, it actually just divides itself. And the process is shown here. It creates more chromosome inside of the cell splits, and then you have 2 cells, and it keeps doing that in sort of an exponential fashion. Some bacteria have an interesting property called, they turn themselves into spores or endospores. And essentially what this does is, if it's in an environment that's not very conducive for it living, it cocoons itself into an outer shell essentially, and makes itself very hardy and robust. So due to presumably global warming, there's a lot of frost that's being melted towards the caps. And you have animals that have been dead for hundreds of years in some cases that had an anthrax infection. They melt out from the ice, and that anthrax is actually still viable and can infect people from being dormant for over 100 years. Which is pretty insane when you think about how things live and die in our society. Spores like that are very dangerous because they can stick around for a long time. So when the anthrax letters occurred after 9/11 in 2001, which many of you might not have been born at that time, but there was a huge scare at that time because we had to decontaminate those buildings because anthrax the Bacillus anthracis, which causes anthrax, can stay alive, so to speak, in that environment for decades. All right, so how are you exposed to pathogens? The sort of things we're going to be dealing with today are inhalation, and with zombies, really they're biting each other almost like a mosquito. But we'll stick to the inhalation example because of COVID-19 right now, and that's an easier thing to discuss. But you can also have, Zika virus was transferred through mosquitoes. There's lots of different viruses that go through that, like malaria. Contact hazards, so people in Africa when people would die from Ebola, sometimes they would go to the funerals, they would touch the bodies as the tradition, and they would get Ebola from the body, which was essentially emitting pathogens. And then you have ingestion and eating things, so every year there's E. coli breakouts from different unwashed vegetables or not properly washed. So there's several different factors here that can cause disease. We're going to focus on the inhalation. So when we start from the beginning of a disease progression, there's several stages that you would go through, and not everyone actually goes through these stages in the same way. But if you start to the far left over here, this is your stage of susceptibility. So assuming that you don't, for instance, have COVID-19 and you haven't had COVID-19, we're all in this stage of susceptibility. We could get COVID-19 if we were out and we did something that got us infected. And essentially, if you went to a point where you were exposed to it and you were becoming infected, you would go into this stage of what's called subclinical disease or pre-symptomatic. You're essentially incubating the disease, but you're not sick yet. You're not showing any signs. And so different diseases have a different incubation period. So there's something like the influenza, which causes the flu, and you can incubate that for maybe a day or two before you actually start feeling sick. SARS-CoV-2, which causes COVID-19, it could be up to 2 weeks before you actually show signs and symptoms. Rabies can be up to 100 days. And then something like AIDS could take years before you actually show signs or symptoms, depending on the dose. And so it really depends on what kind of agent you're talking about or pathogen you're talking about. During this, though, there are some pathologic changes to your body that you might not even know are taking place. In some cases, though, you can circumvent this entire thing and you're what's called asymptomatic, where you don't even ever feel anything, but you are infected and in some cases infectious to others. And then if you do have onset of symptoms, typically what happens is you go to the doctor, you say, I feel sick, they diagnose you with something, and then they start to give you therapeutics to treat that. And so you end up on this right side of here with several different options. These aren't all the options, but these are sort of the classic ones. You could end up dying from a disease, obviously. You could have recovery, but then you're susceptible again. So this is like the flu. You might get sick with the flu, but then you could get sick again. The next season, you could get sick again. And then you could have something like recovery with immunity, like chickenpox, where you don't go back into the susceptible population. Even after recovery, though, some can still spread disease, even though they don't get the disease anymore in the symptomatic phase. And this is sort of the classic example of, many of you might have heard of Typhoid Mary. She was an Irish cook in the early 1900s who had typhoid, and she spread it, but she didn't actually know that she had it. Her mother had typhoid when she was pregnant with Mary. And so Mary was infectious, but did not know that she was infectious. And so for a large part of her adult life, she was actually quarantined by force to stay away from the general public. So as I mentioned, if you are sick, you go and get therapeutics and vaccines. So in this case, we're gonna start on the left side here with therapeutics. These are used to treat a disease. It reduces the severeness of infection. So something like AIDS, you don't actually cure AIDS at this point. You treat it with antiviral therapeutics. And the effectiveness is dependent on the pathogen that you're talking about, the person, the dose, when treatment begins. And in general, the sooner you can start treating yourself with a therapeutic, the better the outcome. So for instance, with anthrax, assuming you have not been vaccinated against it, which most of the public have not, if you don't take any therapeutics and you become infected with anthrax, it's almost 100% fatal. If you take therapeutics after you've begun to show signs and symptoms of illness, it's 40% fatal. And if you take therapeutics before illness sets in, it's 3% fatal. So there's, many other diseases follow a similar trend. It's very substantial, the benefits of going and getting treated if you believe that you've been exposed before you actually get sick. And then there's vaccines, which many of you are familiar with. These provide active immunity against the disease. It usually contains some sort of an agent that resembles the pathogen. So it kickstarts your immune system to say, okay, this is something that we want to fight off. It gets it ready. It's sort of like a machine learning algorithm. It trains it on some sort of a threat, and it says, you know, look for this. It can also be used in some cases as a therapeutic after you've actually become exposed to a disease. And it's been so effective that people have kind of lost sight of how effective it is. It's eradicated many diseases that used to be commonplace, like smallpox, polio, measles, mumps, tuberculosis. I've provided some pictures down here. Jonas Salk invented the polio vaccine, which was a devastating disease for many children across the world. That's a smallpox vaccine line from the 30s. And most of us are accustomed to flu vaccines and getting a flu vaccine yearly. I wanted to give you just a brief overview of some common disease terminology that you might hear so that we're all on the same page. So epidemiology, which many of you have probably heard, is a branch of medicine which deals with the incidence, distribution, control of diseases. Professionals in this are called epidemiologists. The terms outbreak, endemic, epidemic, and pandemic are sort of used loosely a lot of times, but they have more specific meanings. So with an outbreak, if somebody shows up at MIT with Ebola, just one person, that's an outbreak, because we don't expect anybody to have Ebola at MIT right now. So that can be basically a single case. Endemic is something that is regularly found amongst a particular people in a certain area. So if you have a Western African tribe that gets malaria, specifically, or a specific strain of malaria, that's endemic to that particular tribe. An epidemic is something that's widespread in a community at a particular time, whereas a pandemic goes across multiple countries and continents. So we're in a pandemic right now because it is in virtually every country across the entire world. Many of you have probably heard of the reproduction number, R0 or R0. This is going to be critical to the zombie case that we talk about later. This is the expected number of cases directly generated by one case in a susceptible population. So in essence, if you are the only infected person with a disease and you go about your daily business, how many on average are you going to infect? And so if it's 2, then R0 is 2. If it's 3, then it's 3, and so forth. And so that's where that relates. That's the reproduction number. When we talk about SARS-CoV-2, the reproduction number is generally stated as 2 to 4 people. So when you get infected with it, you're going to probably on average infect 2 to 4 other people, who would then infect 2 to 4 other people. Herd immunity is a term that indicates that a large percentage of the population has become immune to an infection, which then provides protection for everyone else. So in this case, you might have 90% of the entire population which is vaccinated against, let's say, measles, and 10% aren't. Those 90% that are vaccinated are providing protection for the 10% that are not vaccinated. And finally, mutation rate is the frequency of new mutations in a gene. So this is important because if you have something like the flu, or influenza, which mutates constantly, you have to come up with a new flu vaccine every year that tries to attack that. Thankfully, it doesn't look as though SARS-CoV-2 is mutating at the same type of rate as an influenza virus. Otherwise, the vaccine that we create for it might be outdated by the time that it actually gets to the point where we can go through the trials. So we have as Earth, we have a history of pandemics that we've experienced, and this isn't slowing down and really changing over time. So on the left is sort of the different pandemics in terms of their size, and on the right is the pandemics as a function of time. You can see that just in a matter of from going from March to June, we went from sort of on the lower end of pandemics historically to the seventh largest pandemic that we've ever had in recorded history. So we're right after the third plague, which was in the 1800s. Clearly, had we not slowed this down even more, it could have gone even worse, even with a low mortality rate because it's so infectious. And historically, you can see that this routinely happens. We should expect that in the future we will have another pandemic. Maybe not in our lifetimes. Maybe several in our lifetimes. Hopefully not. I'll point out that the Black Death, the bubonic plague, was the largest here with 200 million. This wiped out almost half of Europe when it occurred in the 1300s. And this was a movement from rodents with a you would have a flea that would bite that rodent, and the flea would bite a human and transfer the plague between those. Almost 75% of all infectious diseases like this are transmitted from animals, which is why the wet market in Wuhan was such a big deal, and we'll talk through an example here shortly. I've plotted many different viruses and bacteria on a plot with fatality rate or mortality on the y-axis, and then the basic reproductive number, which I just said is the average number that you infect, on the x-axis. You can see here things like measles can spread very rapidly. It's highly infectious. So when somebody has measles and you're in the same room as them, it's very likely you're going to get infected with measles if you're not vaccinated. So on average, you infect 15 other people, 15 to 16 more people when you have the measles or something like pertussis. Whereas anthrax moves through the air, but it doesn't move from person to person. So you might shed some anthrax, some Bacillus anthracis spores that you have on your jacket, but you're not necessarily breathing it out. So it's harder to infect other people with that. However, it's highly lethal if you get it and you don't get treated immediately. And in between, you have things like MERS and smallpox, which have a higher basic reproductive number and a higher fatality rate. With COVID-19, we're kind of down here. It's much more infectious and deadly than influenza, but not nearly so compared to something like smallpox. I've also indicated here with the size, the amount of incubation, so the delay between when you're infected and when you actually show signs and symptoms. And one of the insidious things about smallpox and measles and Ebola is that you can be infected and not know it for a long period of time and infectious to others, which is what helps with the spread. So kind of changing gears here, because reproductive number is going to be critical for the work you're doing modeling zombies in your game, I wanted to talk a little bit about how you spread disease throughout a community, because it's going to be critical to understanding infectious disease in general, and then the spread from zombies running around during this game. So critical things here, and I'm going to cover each one of these with another slide, but the things we think about are, how many pathogens do you need to make you sick? We're talking about one virus? Or are we talking about 10,000 that is necessary? How robust or rugged is the pathogen on air and surfaces? So right now we're obviously washing our hands, cleaning surfaces. Is this something that is very rugged in the environment? With a zombie, the zombie's carrying it and runs over and bites somebody. So it's very rugged in that sense. It's not like you're picking it up from a counter, but most diseases are not necessarily like that. Social measures, so hygiene, distancing, masks, how effective are they and how adhered to are they within society? And then identifying who has been exposed and trying to quarantine them as fast as possible. So if you're sick, removing yourself or doing contact tracing so that you can let them know they might have been exposed to something ahead of time. So you might have been exposed to a zombie. Moving them off into a different area would probably be a good idea before they turn into a zombie. So what determines whether you'll get sick and die? Well, in terms of the dosage, you can get a very small dose and you might have a very small response, or you get a large dose and it's all pretty much inevitable that you're probably going to get sick and die. We have terms here for this. So we call this something that's going to infect about 50% of the population. We call that the ID50 number. And something that's going to kill 50% of the population dosed with it is called the LD50 number. So literally, if you had 100 people in a room and each one was given a certain number of pathogens, the same number of pathogens, and 50% died from it, that's your LD50 number. And so they do animal testing similar to this to establish some of these different things for infectious diseases. On the right side here, I've provided for anthrax how they've derived the LD50 number, or in this case, sorry, the ID50 number, so the amount of infected from a certain number of doses. So in this case, this is probability on the y-axis. It's a logarithmic scale. At this 50% probability mark, I've drawn a dashed line, and then you move down to the number of spores on the x-axis, and you have 11,000 spores that are needed on average to infect someone with anthrax. And there's been several models that have been fit to this because we have a limited number of humans that have actually been exposed to anthrax. So the limited data that we have, we've tried to fit several different curves through it. Some diseases have more data, some diseases have less data. If your immune system is poor, if you're immunocompromised, sick already, or say you have severe chronic heart disease and you get sick, it may only take 10 spores to kill you. So that all of this changes depending on how healthy the individual is. I mentioned anthrax earlier, 100% fatal if not treated. However, things like COVID-19, 81% of the cases roughly are mild, 4.7% are critical. And this jumps up if you are older in age or if you have different types of diseases or multiple diseases at the same time. Quickly touching on the aerosols, because I talked a bit about person to person and focusing on inhalational concerns with infectious disease here. I just wanted to point out that the reason why the masks are occurring and the reason why people are trying to distance themselves is mainly through this aerosol phase. So this is anything that a solid or a liquid that moves through gas, that's an aerosol. And so different things that you do, like breathing and talking, coughing, they will shed more or less particles. So down here in the lower left corner, I've given you an indication of the number of particles that are exhaled on average. This is from one experiment, so take it with a grain of salt, but it gives you a relative amount of particles per liter of air that are exhaled from these different activities. So breathing was about 98 particles per liter of air, whereas when you go to the doctor and you say, you're breathing out about 10 times more particles than when you're just breathing at normal rest. Singing actually sheds as many particles in some cases as coughing. And so there have been accounts of people becoming sick with COVID-19 from choir practices in enclosed environments. It's a heavy shedder of particles. On the middle here, I've plotted particles per cough from an experiment. You can see there's a lot of small particles. By small particles, I mean below 1 micron. That's very small particles. And so this gives you an indication, a diameter of 0.9 microns gives you this volume. With just one 9 micron particle, you have 1,000 of these smaller particles that equal that volume. So these particles here, kind of in the 2 micron and above, that's what we're trying to really tamp down with most masks. These are sort of sneeze and cough guards. And so, just one of these could do a lot of damage if somebody were to cough towards your direction. To give you perspective, SARS-CoV-2 is around 100 nanometers in size. 1 million of those can fit inside of a 10 micron droplet. It's a lot of infectious dose that could hit you from one of these. So, I also mentioned survivability on different air and in the air and on surfaces, but it's a very highly variable process. So when I talk about survivability, I'm saying, can it still infect me if somebody coughed on this countertop and I touch it? And that depends heavily on the fluid that was coughed, so blood, saliva, mucus, that sort of thing. Many of you are aware that high temperatures, sunlight, particularly ultraviolet exposure, and dryness or desiccation over time can inactivate or essentially kill the pathogen, so to speak. And I provided some examples here of different pathogens and the disease that they cause and the survivability in air and surfaces. So Ebola, for instance, the survivability is low in air. It needs generally blood or saliva to survive. If it is in blood and it's encapsulated, it can survive for quite some time on a surface. But typically you wouldn't be touching blood. Hopefully that was observable on a surface. Measles and influenza, these two can survive for a few hours in the air and on surfaces. So if you're around somebody, they can infect you just from breathing in the same office for an hour or two. COVID-19 is sort of hours to days. It has a longer survivability, particularly on surfaces. And then something like Bacillus anthracis, as I mentioned, can survive for years in the air and on surfaces. So from the aerosol standpoint and the survivability standpoint, many of you are obviously aware of, we have a 6-foot social distancing guideline right now in place. And so I thought it might be interesting on this topic to say kind of where did that come from? The World Health Organization, the WHO, actually recommends 1 meter. That was based on work that was done many years ago on tuberculosis, and they looked at where sneeze droplets land, and it's typically within 3 feet. So the big particles that I mentioned before, they land pretty quickly. Small particles, though, sort of in the 5 micron and down, they take 40 minutes or longer to land if they were aerosolized from a sneeze, cough, breathing, singing, that sort of thing. So the CDC guideline is, many think, is based on a 2003 journal paper about flight infections with someone that was infected on an airline that had SARS. On that airline, about 22 other people became infected. 8 people in the 3 rows seated in front of the infected passenger. So over here on the right, this is the infected passenger here at this cross. And then the infected passengers, as a result of this passenger, you can see are the solid squares. So you can see that it's obviously sort of right here in the rows up here, but there are other people behind and on the sides that also became infected. A little bit of a kind of randomness to this. I will say that from the studies, sort of comprehensively, that have looked into infectious disease, in general, a physical distance of greater than 1 meter results in a large reduction of virus infection. And that for every 1 meter you space yourself out and distance yourself, it increases it reduces your risk by 2.02 times. So physical distancing works, but there is some randomness to this. And so that's where the 6-foot guideline comes in. And even that, in some cases, is not going to be good enough if you're in a confined space. Masks are a big part of our society now. And the reason why is it reduces the number of viral particles and pathogens that are shed from you and that you're inhaling. But something to keep in mind is that it's important to have high filtering capabilities, but also that it's a good fitting mask. So even a poor mask, though, can act as a sneeze guard with those big globules that I mentioned before. I provided different mask types and the filtration efficiency that you would expect. Notice here that if you have an N95 mask and it's worn properly, it pretty much gets rid of 99.9% of everything. But if you have a small gap on the side, because it filters so much in there, the air wants to move around that. And so it reduces rapidly the effectiveness of the mask, only 12% effective if you have a gap on the side of that N95 mask. So just be aware of that. One of the reasons that N95 masks work so well is that there's a middle layer to these that are electrostatically charged that still allow air to pass you, so you to breathe easily in them, relatively easily. But then trap particles using the electrostatic feature. The particles are attracted to that. And then I mentioned testing and contact tracing as a means to try and identify quickly who's been infected and get them removed from the regular general society. With testing, generally you use some sort of a body fluid like saliva or mucus, and you put something under a microscope or culture it. You can also use things like PCR, which many of you probably have heard of. I will mention that testing is imperfect. It's prone to error. You have to understand the results, and it's fairly slow in most cases. So The other thing I'll point out is that many of the tests that we have now, they may say that there was viral RNA there. So you could say there was SARS-CoV-2 viral RNA in your nose. That doesn't mean that you're infected, and it doesn't mean that you're infectious. It just means that there's viral RNA in your nose. So keep that in mind. Also, the way that you would know whether it was infectious is they essentially take a plate of live living cells, they stain it crystal violet, they then infect it with something like SARS-CoV-2, and these little dots are where SARS-CoV-2 has killed that living cell, and then you know that, yeah, it's killing cells, and so it's infective. A contact tracing has been, on the right side, that's been the most traditional method that has been used in the past when we didn't have a lot of the technology that we have now. It's still very effective. People are working on using smartphones and GPS and other things to do it. But the thing that's tried and true is public health interviews. So if you come into the hospital and you are diagnosed as sick, they're going to have interviews that say, okay, so who have you been in contact with in the last few days? And then they'll contact them and do the same thing, and they'll run down this network of different people. It's obviously time intensive, but it's highly effective, and one of the reasons that we were able to eradicate smallpox. All right, so let's get to the modeling. Let's wrap up with modeling, because I think that's ultimately going to help you guys be able to do your modeling in your game for the zombies. As an example here, I've shown the models that are an aggregate model from all these different universities and labs for COVID-19. You can see that this is real data here, and then you get to June. Again, this is a month outdated. But you see all these different modeling estimates. And so the question that we're going to cover is, where are they getting these? And these are all, for the most part, compartmental models. And that's what you're going to use for your zombie game. And I'm going to cover that, but I'm going to go through that kind of slowly and give you some comparisons to others. So to start off with, there are things other than compartmental models that you could model infectious disease with. Sort of on the opposite side of the spectrum would be something like a physics-based model. And what I mean by that is you embed air movement, geometry, talking, breathing, the exact mass setup, the exact person setup in a room. So I've taken a generic conference room here. This is a table. This is an infected person at the table. You have an HVAC supply and an HVAC return. This is where your air comes in from your air conditioning, and then it's pulled out and reconditioned. You have a doorway to the room. And so this movie here shows you, I ran this using a computational fluid dynamics program that actually tracks the exact movement of the viral particles being shed from someone's breathing and coughing in the room. And you can see this sort of tortuous, complex path that they're taking. And if you're in the room, you could see where these are going as well. And so that gives you an idea of kind of the complexity that you could add into this to look at the risk to others. And this would be something that you would want to use to answer a very specific question about risk. Whereas a compartmental model, which we'll go to the next slide, which covers this, it's a simplified model of infectious disease. It avoids the physics, it runs faster, and people are essentially assigned to compartments. So you're either, susceptible, you could be exposed, you could be an infected person, a zombie in your zombie game, recovered, you could be deceased. There's all kinds of different compartments that you could be placed into. And so you essentially set up these fairly simple differential equations to solve, these deterministic equations. You're able to embed some randomness or probabilistic approach to it, stochasticness. You don't have to, but it is an option. Several different variations of the compartmental models exist for public health departments. The one that we're going to focus on today, because it has direct applicability to your zombie game, is the SEIR model. So you would be either in a susceptible compartment, exposed, infectious, or removed. Removed being dead or recovered. And so this is a simple model where you see people moving from susceptible on the curve. Some go into exposed. You go from exposed to infected, infected to recovered. And in this case, you have a small enough population, everyone essentially goes from susceptible to recovered. So these are the compartments in a very basic fashion. You're in one of these four compartments when you're in the model. And so susceptible to exposed is just exposed is the number of people that have been exposed, but they're not showing signs and symptoms yet. Infected is now they're infectious and signs and symptoms. And like I said, removed is recovered or dead from the disease. So how do we go from susceptible to exposed? And so the way that they do this generally is they assume that you have a well-mixed population. They actually call it the law of mass action. So it's sort of like you're mixing chemicals together in a reaction. And so they're assuming everybody goes out to the park and you're mixing and matching, and every infected person, I1, I2 through IM, mixes and matches with every susceptible person, S1, S2 through SN. So the number of interactions are S times I. And the probability essentially of those becoming actual infections is this beta term. And the beta term is called the infectious rate. And it's the R naught number, that's that reproduction number again, divided by the average duration of the infection, D. And so this is why that R naught number is so critical to moving from these different zones. So S to E is with this differential equation, ds dt equals negative beta times S times I. So then how do we move from exposed to infected? Well, now we add in this term over here to this term, because that's the number of people that are entering into the exposed, and the number that are exiting out into the infected region is this sigma times E, sigma being the incubation rate, or how long it takes to go from the exposed to the infectious period of time. And then to go the infectious DI dt, you have the sigma E, which is added in from this side. And then you have this term here, which gives you the recovery rate times the number of infected individuals. And I'm guessing this might, if you haven't seen these terms before, it might take a little while for you to kind of process, okay, why is that this? And if anybody has any questions about it, I'm happy to go through it. But these are basically, you're just kind of stepping through and assuming that you have things moving from one compartment to the other. And so you're adding in those different terms to give you the rate. And then finally, how does the removed compartment change? Well, you have these different people that go through this recovery phase. And so you have a recovery rate that is multiplied by the number of infected individuals. All of these are fairly commonly known items. And so we'll go through an example here in a second, but I wanted to roll all of this up into one chart so you get an idea of kind of all the terms that you need for the SEIR model. So this is the infectious rate, the incubation rate, the recovery rate, the four different models, the four different compartments, and then their terms, and then the four differential equations that need to be solved in order to create one of those susceptible exposed infectious recovery charts that I showed you. So I've provided an example here of the Wuhan city example, where you essentially have 11 million people in Wuhan city to start out with in the population. 800 people assumed to be initially exposed, 40 of those become infected. So you get a sense here of kind of the size to start out. And then you can say, okay, well, if the average incubation is 5.2 days for SARS-CoV-2, and the average recovery time is around 18 days, and you know what you can make some assumptions on the reproduction rate, then you can plot these out. And so this top plot is the reproductive number of 2. So every person on average infects 2 other people, 4 other people, 8 other people. And you can see that when this peak of the infections come in, so in the case of reproduction number 2, you have 500,000 people sick at one time. With 4, you have 3.5 million people sick all at once. And with the reproductive number of 8, you have 5 million people sick all at once. Many of you have heard about flattening the curve with COVID-19. And the reason why that's so important is these peaks, 3.5, 5 million people sick all at once, many of those presumably will need to go into some sort of intensive care. That will exacerbate your medical system and make it harder for even heart attacks to get serviced, because you have so many people that are sick all at once. I'm going to point out that there is code available for free to do all of this in both MATLAB, Python, and R. at this website here. It's a great resource for you to look through it if you want a further understanding. They go through how to model these SEIR model, and they have other compartmental models for you to look at. Another great online resource that I would encourage everybody to look at is the online epidemic calculator. So the website's provided here. You can go through and customize your population size, reproduction number, incubation time, etc. Essentially, you can toggle these things around on the bottom here, and this thing will move in near real time. You can also change your R0 over time. So let's say you start out with no social distancing in place, and then you change to an RT so that the reproductive number goes down to, say, by half. And you can see what that does to the number of infections. You can also check this with your game to see if you're getting the right results based on your zombie numbers relatively, assuming that zombies are just infected individuals. Okay, so zombies. Very briefly, this is the zombie model that I believe that you guys are going to be using, or that I would at least cover something close to what you guys will be using. In this case, I've added in a birth rate. So if the zombie apocalypse happens over a long enough period of time, you'll have babies that are being born into society that are now part of the susceptible population that could be bitten by zombies. I've also added in here this term delta that would allow you to model people just dying from, say, natural causes, not necessarily from zombies or infectious disease, but they just die. The cool thing about the zombie model, though, is that you go through all the way to the end, to the death, or you know, the dead here, but you can go back into the zombie compartment, right? Because you move back and forth between the dead and being a zombie in some cases, so they can rise back up. So somebody could die from natural causes, but then a zombie could attack them and turn them into a zombie. And so I've provided here the differential equations that you would need, which is very related to the SEIR model, very similar in terms of the nomenclature, except the birth rate's been added in and natural death's been added in, depending on the sophistication of the game. You can also take those out if that's not what you want. So in summary, I hope I've provided you with a nice beginning to some of these processes and how complex and variable they are. Much depends on the pathogen type, environment, individuals, and social measures that you put into place as to how it spreads. We've only touched sort of on the tip of the iceberg here, so I'm happy to answer any other questions that you might have over time or related to the game, more specific to zombies and characterizing some of that. Models exist with different levels of resolution and fidelity, and so you have to ask yourself, what are the questions that I'm trying to answer? How much do I need as far as detail in order to answer that question? There are a lot of great free online tutorials, videos, and courses related to infectious disease and modeling. One of the ones that I would recommend if you're interested in this topic in general is a Coursera free course called Epidemics, the Dynamics of Infectious Diseases. It's taught by Penn State. It's a great course and it's free. And there's an awesome YouTube video called Simulating an Epidemic, which kind of steps through all these SEIR and other compartmental models and does some kind of small scale experiments in real time so that you can watch that. And with that, I believe that that's all I have for the slides. And I think that leaves us with 10 minutes or so. I don't know how you guys typically do this. Do you guys take questions, or do you guys want to get rolling with something else?
Yeah, we have some time for questions. I think there's one in the chat right now. Are there any notable diseases that clearly haven't followed the common models for disease spread?
Not that I know of. I mean, to that point, there are tons of different variations to the compartmental models to capture the essence of all of the different diseases. So in essence, you would just change around your compartments if things move differently. So you can have things where people move. So you might be exposed and then all of a sudden not symptomatic and go back into susceptible and then move around. So you could have the arrows moving in different directions. You can have it circumventing it with a certain probability. So you can change that to fit generally whatever disease characteristics that you would like. Any other questions? I see a question here from Alex. Does having two notable diseases affect the model in any super important way? So if you were, let's just say you had chronic heart disease or diabetes. Let's say you had both, and you get infected with SARS-CoV-2. It's going to change your different characteristics that you go through that. So the chances of you having complications, more prolonged infectious period, more severe symptoms, and mortality would be increased. And so what you can do if you wanted to, so let's just say some people were more susceptible to zombies than others. You could create a probabilistic decision tree where you say 10% of the population is highly susceptible to zombies, 90% are not, or whatever you'd like. And so you could basically set it off to where you give a dice roll to those that are more susceptible, and that allows for a better reflection of reality in that case. So hopefully that works, but it would exacerbate the chances that you would get the disease. You would get the disease and that you would have a severe symptoms from it. Any other questions?
Oh, well, thank you very much for that talk. It was a great talk, Ben. I really appreciated it, and I think our students really definitely did. Yep, you're getting thank yous in the chat.
Awesome, no problem. And if anybody has any follow-up questions related to modeling the zombies or something along that lines, I'd be happy to circle back with a group to discuss that.
Awesome. Thank you very much again, Ben. Okay, everybody.
Thanks. Good luck, everybody.
Have a break until your Athi and Chris have Q&A time coming up.
Sweet.
So that's a break until 11.
Yep, break until 11.
I have my cat.
Yes,
Hi,
there is
Mimi.
cat. Wow,
Well, she
Mimi's
can
pretty
Mimi.
big.
Yeah, she's a big.
She is a hefty cat.
Yes, it's nice to have solid chunk of cat.
My
my
cat
cats
left
are-
me.
My
He
cat's
was in the bed, but
Oh, you've got
On-
McAllen?
no, he's
Joel's got
gone.
McAllen.
He's
Oh.
always, yeah, he's always within a foot or two of me.
He's a big, huge, dark fluff ball.
It's
Yep.
cute.
It's too bad you
It's the
can't see the
black
cat
hole.
magnetism experiment that Joel does.
Oh yeah,
Cat magnetism.
Yeah, it's hilarious. He puts
the
the
cat
cat
is like
within
a
like
yeah.
paw range of what, you know, like
The cat tree.
cat tree, and the cat just like the paws come out and just start
Yeah.
flailing, and then you back away and it goes down, and you get close and the paws come out. It's really cute.
Yeah, within like 2 or 3 feet of the cat tree, the cat just would rather be on it than you holding it.
That's extraordinary.
So, and it's like, I even tried like hiding the cat tree from its view. You know, walk by, having the cat facing the other way. But I think it just knows, and it will like bend over backwards, like reaching for the cat tree.
That's awesome. Juno wants video.
Yeah, I'm not big on documenting